Whether you're a bioprocess engineer hunting for the perfect scaled-down model, a biotech founder architecting the leap to commercialization, or a scientific analyst who craves raw technical truth, you've reached the technical edge. In this space, we live by a single mantra: the process is the product. Welcome to the Biomanufacturing and Fermentation Technology podcast with Prasad Ernala. Hit subscribe and ring the bell to join a global community and stay at the vanguard of biotech translation. Let's build the bioindustrial future together.
I want to start today with a quote from our source material that really, it hit me hard. It's a bit of a cold open, but I think anyone who's ever worked a night shift in bioprocessing is going to feel this one.
I think I know the one you're talking about.
The quote is, "Downstream is where confidence goes to die."
It's brutal. A little dramatic, maybe, but honestly, it's incredibly accurate. It captures that feeling on the plant floor perfectly.
It just paints this picture, right? You're in downstream processing, DSP. Upstream hands you a harvest. They say, hey, great news, everything looks normal.
The bioreactor run was perfect. You hear that all the time.
Exactly. You take the handoff and then just chaos.
Right. All of a sudden, clarification is taking twice as long. Your filters are blinding way, way too early. The capture column breakthrough just looks weird.
And that ultrafiltration step, the one that's supposed to be routine, or, done by the end of the shift,
Yeah.
suddenly it's an all-night babysitting job. You're just stuck there, watching the schedule absolutely melt down around you.
And when that happens, the reaction on the floor is, well, it's almost Pavlovian, right? It's this scramble for answers.
Everyone starts asking the same things.
Did the resin age out? Is the column dead? Did someone mess up a buffer prep? Or, my personal favorite,
Oh, I know this one.
is upstream drifting again.
That one's usually the loudest, isn't it? But that really is the core of what we're unpacking today, because the reality is these DSP failures are almost never just one thing.
No, it's never a single point of failure. It's what the literature calls a variability chain.
A variability chain.
Exactly. It starts way back upstream, sneaks through the harvest, and then it surfaces in a chromatography trace days later, and you're left with a yield loss nobody can quite explain.
So our deep dive today is on downstream digital twins. But we need to be really clear. We are not talking about, cool 3D graphics on a screen.
No, this isn't about sci-fi visualizations.
We're asking a very specific operational question. If we build one of these, does it actually reduce that variability?
That's the key. Does it shift us from that reactive firefighting to something genuinely predictive? Or, and this is the cynical take we have to explore, does it just help teams assign blame faster?
That is the mission for this deep dive. Are these tools solving the physics, or are they just documenting the disaster with more detail? The source material says that DSP is still often run like a craft.
It is. It's artisanal. You do some scouting runs, you lock a recipe, and then you spend the next year just reacting to every little drift.
So I want to explore how we get away from the craft and into something truly engineered.
I'm with you. But we need to ground this conversation right away. There's a huge gap between academic optimization and manufacturing reality.
What do you mean by that?
Well, in a lab, you're optimizing for a perfect peak with a clean synthetic feed. In manufacturing, you're dealing with messy biological feeds, equipment that's slowly degrading, and immense time pressure. You have to release the batch.
So the lens has to be, does this actually work when the pressure is on and the feed is, for lack of a better word, ugly? Okay, let's get into the mechanics. The literature talks about building twin primitives, which I have to admit sounds a little strange.
It does, but it just means building digital components for specific unit ops. One for clarification, one for chromatography, one for UFDF.
Right, and what's interesting is you're saying the value isn't in some big, flashy overview of the whole plant.
Not at all. The real value is in predicting the boring constraints.
The boring stuff.
The boring stuff is what burns your budget. We're talking about things like filter area sizing mistakes, or predicting the exact moment a chromatography column is going to start drifting, or nailing the endpoint of a diafiltration step so you don't overshoot and dilute your product.
Why is a digital twin better at that than, say, a senior operator who knows that skid inside and out?
Because right now, even the best operators often have to rely on guesswork or static recipes. They run for X minutes or Y volume. A digital twin can do something called data coupling.
Data coupling. Unpack that for us.
It just means the twin is looking at multiple variables at once, in real time. It sees the pressure trend and the flux trend together. It's calculating the resistance of the filter cake as it's forming. It can see the subtle curve in the data that a human eye might miss until the alarm is already screaming.
So it can predict a critical failure, like the pores blocking up, way before it actually happens.
Hours before it destroys your schedule, in some cases. That's the shift from reactive to predictive. But, and this is the huge reality check, these primitives are useless if they ignore context. You can't just model the unit up in a vacuum.
What's the context?
You have to look at holds.
Holds, as in just holding the material in a tank.
Exactly. Process engineers always underestimate the physics of the hold. Imagine the harvest finishes on a Friday afternoon. It goes into a tank, and it just sits there until Monday morning.
Okay.
That whole time, those temperature swings, they change the material properties. The viscosity can change. The impurity profile shifts. Things start to aggregate, to clump together.
So the stuff you're putting into the process on Monday is fundamentally different from what came out of the bioreactor on Friday.
Yes. You've changed the boundary conditions. If your twin thinks it's getting fresh harvest, but it's really getting 72-hour-old, slightly aggregated harvest, all of its predictions will be wrong. It fails because it ignored the plant schedule.
This connects directly to the next big point, the variability chain. This is where that tension between upstream and downstream really comes into focus.
Yes, the idea that downstream problems rarely start downstream.
Let's talk about those boundary conditions. For downstream, the harvest properties themselves, we're talking viscosity, conductivity, the amount of solids, those are the hard limits.
They are the absolute design constraints. You can't process what you aren't given.
But the upstream team, they don't always see it that way, do they?
That is the fundamental disconnect. Upstream is often incentivized to maximize titer, how much product is in the tank. They might see viscosity and conductivity as well, byproducts.
Just a side effect of getting more product.
Exactly. The attitude could be, hey, we boosted titer by 20%. The broth is just a little thicker. Downstream will figure it out.
But for the downstream engineer, that thicker broth is a complete nightmare.
It's a design constraint violation. If upstream changes the salt concentration or adds a new antifoam to get more product out, they've completely changed the loading conditions for every single filter and column that comes after.
So if you have a downstream twin that doesn't talk to an upstream twin?
It's useless. It's flying blind. The twin is assuming a standard feed when the feed is actually completely different. This is why you cannot optimize these things in silos. The twin has to span that gap.
Okay, so let's say we have the data. We know the feed is messy. How do we model this? The source talks about the difference between mechanistic models and hybrid or surrogate models.
Right. Mechanistic models are based on first principles, physics, chemistry. They are incredibly powerful for explaining why something happened.
That sounds ideal. It's a physics engine for your process. What's the catch?
They're computationally heavy. Very heavy. Solving all the equations for a complex chromatography run can take hours. If you're in the middle of a run and you need to decide in 5 minutes, you can't wait 2 hours for the computer.
It's the difference between a supercomputer and a stopwatch. You need the stopwatch.
You need the stopwatch. And that's where surrogate models come in.
How do they solve the speed problem?
Well, they use accelerated solvers. They're still built on those mechanistic foundations, so they understand the physics, but they're simplified to run fast enough to make decisions while the pump is still running.
That sounds like the holy grail for process control. But the notes here highlight something called a governance risk. That sounds ominous.
It's a huge hidden risk. It's about human nature. Let's say a surrogate model starts to drift a little. A data scientist might be tempted to just say, oh, I'll just retrain it on the latest data, fix it on the fly.
That sounds proactive. What's wrong with that?
Because if you just retrain it without a process, you've changed the basis of your decision tool. You've moved the goalposts. You might be masking a real process drift, like the column is failing, by just adjusting the model to accept the new reality.
Ah, so you can't tell if the map is wrong or if the actual territory has changed.
Exactly. You need a controlled life cycle for model updates. You can't have a fix-it-on-the-fly culture.
That brings us to what I think is the most detective-like part of this, root cause analysis. Using these twins to figure out what went wrong after the fact.
This is a massive value driver. Instead of a bunch of engineers in a room speculating, I think it was the buffer, I bet it was the pump, you use the twin for what's called in silico testing.
In the computer.
Right. You take your out-of-spec chromatogram, it looks weird. You feed that data into the model. Then you start asking it questions. Model, does this look like resin aging?
And it runs a simulation of the crime scene.
It does. It tests your hypotheses. It can virtually degrade the resin in the model and tell you, no, that doesn't produce the weird peak you saw. Then you ask, does it look like a buffer deviation? And it can say, yes, that fits the data.
But there's a trap here. The data trap.
A huge trap. This only works if your event capture is robust. Imagine an operator on the floor switched to a new buffer lot. But they didn't scan it into the digital record. They just jotted it down in a paper logbook.
The model has no idea the buffer changed.
It's completely blind to it. So when you ask the model what happened, it can't see the real cause. So it defaults to the only variable it has left that might fit the data, which is usually resin aging.
So you end up blaming the resin for a simple buffer mistake because that mistake wasn't digitized.
Precisely. And speaking of resin aging, we need to be clear, it's not just a number of cycles.
It's not the odometer on a car?
Not at all. It's the exposure history, the fouling load, the quality of the cleaning, any abuse events, like a pressure spike. The twin needs to know the history of the abuse, not just the cycle count.
That's a critical point. But let's zoom out. We've talked tech, models, physics, but the source drops a bomb near the end. It says the biggest barrier isn't the technology at all.
No, it's organizational incentives.
The co-twin barrier. Explain what's going on here.
It's classic corporate silos. Upstream teams are typically incentivized on tighter and time, how much product, how fast. Downstream is incentivized on yield and purity, how much you save, and how clean it is.
And those goals are in direct conflict sometimes.
All the time. Upstream might hit a huge tighter goal by creating a harvest that's, full of debris and impurities. They win. They get their bonus. They throw that material over the wall to downstream.
And downstream is left holding the bag.
Their yield drops because the filters clog. Their purity suffers. They look like they're failing because they're being measured on yield and purity.
So if you install a digital twin in that environment without fixing the incentives,
the digital twin just becomes a very sophisticated blame assignment tool. The downstream team uses it to prove, mathematically, that upstream send them garbage. The twin doesn't prevent variability, it just helps you argue about who caused it with better charts.
That's incredibly dysfunctional, but I'm sure a lot of people listening are nodding along right now.
The only fix is shared KPIs. You have to design upstream processes with downstream constraints in mind. The twin has to optimize for the global yield, not just one department's output.
Okay, so let's shift to a design review. What are the practical takeaways? The source suggests starting with harvest fingerprinting.
This is a great first step. Don't just accept the harvest blindly. Fingerprint it. Measure the solids. We get a proxy for viscosity. Measure the conductivity. Do it before you start the run.
So you know what you're up against before you even open the valve.
Exactly. Use that fingerprint to predict the pain. The twin can say, warning, viscosity is high today. Your filter flux is going to decline faster. Adjust your plan now.
And what about drift detection?
Look at the unglamorous signals. Everyone stares at the product peak on the chromatogram, but the first thing to drift is usually pressure and flow. If your column back pressure is creeping up run over run, that tells you something is changing.
And that affects residence time, which is critical.
It affects everything. The twin has to monitor those boring mechanical signals to catch the drift before it becomes a batch failure. It's the check engine light.
So let's circle back to our core question. Is this really shifting us from reactive to predictive?
I think the answer is a qualified yes. We are seeing it happen. These hybrid models are enabling earlier detection. We can catch fouling and break through drift before the yield is gone. That's real.
But the qualification is the connection.
The caveat is you cannot do it in isolation. You have to connect upstream data to downstream models. You have to treat the process as one continuous chain.
The ultimate goal mentioned in the source is real-time release.
That's the dream. Releasing a batch based on the process data and the model's predictions, not weeks of offline testing.
But that requires a level of trust in these models that is, frankly, terrifying for a lot of quality departments.
That requires models that are defensible, transparent, and most importantly, honest about uncertainty. A model can't just say pass. It has to say pass with 99.8% confidence based on these specific variables.
That's a very high bar.
It is. But like we said at the start, downstream is where confidence goes to die. If we want to bring that confidence back, we need models that tell the truth, even when it's messy.
I want to leave our listeners with one final thought from the source that really stuck with me. It's about the nature of the process itself. You can be optimistic. You can hope a column lasts one more cycle.
Hope is not a strategy.
Right. As the source says, the process does not forgive optimism. It invoices you for it.
And that invoice usually comes due at 3 in the morning on a Sunday.
Isn't that the truth? So for everyone listening, think about your own models. Are they honest about uncertainty, or are they just optimistic? That's it for this deep dive. Thanks for listening.
Take care.
Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala. Thanks for listening.